During the project, we attempted to provide sentiment analysis for the dataset so that the real-world applicability of our methods could be tested. Sentiment analysis was used to score the descriptions in every rental listing and used the scores as a new feature. Over 40,000 sets training data made it difficult to label the description manually with sentiment orientation and even harder to score them. Therefore, we did not label the description manually and used unsupervised learning instead. Before we started, we did some preprocessing to the text. We replaced all punctuations and numbers with space since the description contained lots of irregular HTML tags, numbers, and punctuations. We also used stop words provided by NLTK library to filter common English words. Although these words can be good indicators, we would like to score the words closely related to the positive and negative vocabulary and let them indicate the sentiment orientation. So finally, we filter out low-frequency unigrams after extract them and only use these to build a set of collocations. Next, we use existing sentiment lexicons for scoring. The score of a description is determined by the number of positive words and negative words found by the lexicon. We imported opinion lexicon proposed by Bing Liu and sent T-WordsNet and compare the effects. The result of adding these features showed no improvement to our classifier accuracies, which led us to stop the unsupervised learning approach. We then decided to use the algorithm proposed by Peter D. Turney in 2002 to score the semantic orientation of description, which is based on the pointwise mutual information algorithm. We defined positive and negative vocabularies and used them as seeds to calculate the PMI of each word in the vocabularies and those in every descriptions. By summing PMI words in a description and the words in positive and negative vocabulary, we got the positive and negative association scores. The difference of positive and negative association score can represent the sentiment orientation of a description. Unfortunately, this new feature also had no visible changes to the accuracy of the classifier. At this point, we stopped attempting sentiment analysis. We learned after the contest that many competitors did not use sentiment analysis either, so we still consider the data we use to be applicable in real-world situations.
To establish a baseline to compare automated methods, the team trained 5 different classification algorithms with 5 different feature selection algorithms. One contained all features, 3 were selected with the techniques we tested earlier, and one final feature set included only the features in common from those 3 selectors. The 5 classifiers were a basic 5-layer feed-forward neural network with no special tuning, an extra trees and a random forest classifier, which were reviewed later in class, an extreme gradient boosting classifier, which is similar to a gradient boosting support vector machine but with hardware acceleration built in, and final, a stacking ensemble classifier, which takes output from 4 other classifiers, feeds this through a final gradient boosting classifier. The XGBoost library was chosen primarily due to its preeminence in Kaggle computations. Using the stacking algorithms were implemented because generally these will produce better results than any single classifier. The default parameters for these classifiers were used whenever possible to avoid hand optimizing these parameters. This chart shows the cross-validation multi-class logarithmic losses of the 5 classifier with 5 feature selection methods. Some of these results were surprising. First, the neural network performed poorly relative to other classifiers. The team was anticipating that this algorithm might be able to demonstrate some degree of automated feature engineering that is inherent in how neural networks operate. Instead, the accuracy of the neural network decreased as the number of features increased. This likely cause of this is the heterogeneous nature of the datasets. The combination of sparse and dense fields likely means that the nuances between features could not be recognized or were overfitted. Another surprise was that XGBoost also performed poorly. Some of the highest-ranking members of the Kaggle competition confirmed that they were using XGBoost to get their results. For our analysis, this actually was the least accurate algorithm from our baseline model.